which I have written in collaboration with Shokamata, Maurizio Martinez, and Michał Spaniński. So let me set the stage somehow. So a far for equilibrium attractor is a concept that has been already mentioned a few times in this conference. So I will, by that concept, I will loosely understand a property of the system where the initial memory of the initial conditions is swept away on a very short time scales. On a time scale where the system is essentially still far from equilibrium. So essentially, it's a model, it's a way to model this orange region here in the heavy ion collision, which connects the initial stages and the hydrodynamic evolution. So once the system is dragged towards the attractor, which is off equilibrium stage of the evolution, then this off equilibrium universal dynamics drags the system towards the hydrodynamic description. So as seen in this way, it's a rather transparent, though approximate way to connect the initial state with the start of the hydrodynamic expansion. And this property has been observed in a number of models, essentially hydrodynamics model, which is the Miller-Israel-Stewart theory and extensions thereof, which was mentioned by Michał, in kinetic theory, both in the relaxation time approximation as well in the Fokker-Planck limit, and then in holographic models. So there are a few questions which one can answer and which I will address in my talk. So first is what is the mechanism, the physical mechanism that drives the system towards the attractor? Can the attractor have the experimental imprints? And if so, how much can we, using the experimental data, how much can we constrain this pre-hydrodynamic flow and in consequence, the initial stages of the heavy ion collision evolution? So that will be the focus of my talk. I will use the Bjorken flow symmetry assumptions for most of the time. Tau is the proper time. Energy momentum tensor admits this diagonal form. I will assume conformal invariance, so tracelessness and conservation, which imposes that the system is determined by one function, the pressure anisotropy. I will also use the notion of the effective temperature, which is defined here. It's not the true equilibrium temperature, it's the effective temperature, and the famous W variable, which is time, the proper time measured in the units of relaxation time, which is essentially a ratio of the macroscopic scale of the system, which is tau, to the microscopic scale of the system, which is the relaxation time, which is the inverse Knudsen number. So as W goes to infinity and time progresses, Knudsen number goes to 0 and W to infinity, then we can expect the system admits a hydrodynamic description. So now the conservation equation, it can be cast in this form. And essentially, in dimensionless variable, it's written in here. So there is a simple solution to this equation. The solution evolves initial temperature towards the late time. And it might be deceptively simple, but all the information about the system is hidden here in this anisotropy function. And first of all, it contains information about the initial data, initial conditions, apart from the initial temperature. And also, we don't have equations of state of equilibrium. That's why we need some way to model this A of X. So one can use, for example, some microscopic model. So all the complicancy of the dynamics of the system is hidden in this anisotropy function. So, and also the initial conditions. So a microscopic model. So let me illustrate my concepts with the microscopic model is Miller-Israel-Stewart theory. So here you see the plot of this pressure anisotropy as a function of time for various initial conditions. And here the attractor is very simply defined as the only regular solution at W equal to 0. So this concept in this model, this concept is very clear and very easy to define. But it's all about the initial conditions and about the late time behavior. However, in more complicated models, it's not clear how to define this general attractor line, as it is not obvious which initial conditions to choose. However, in this simple model, the attractor exists and it drives the system towards the equilibration. And now, despite the definition, one can ask a physical question. So what is the mechanism that drives the system towards the attractor. So this can be answered. So at early time, there are two mechanisms. At early times, the system is dominated by the expansion. In the Bjorken case, the expansion rate is much faster, and it overtakes any scale connected to the interactions. So this is the expansion-dominated region, where the expansion drags the system towards the attractor. And then we have the universal power law behavior at early times. But this is symmetry determined. So this mechanism depends strongly on the Bjorken symmetry assumption. In contrast, at late times, the dragging mechanism towards the attractor is the decay of the non-hydrodynamic mode, which is usually an exponentially damped mode. For example, in the MIS theory or in the holography, there are purely exponentially damped modes. And this is generic. This is symmetry independent. This is responsible for this divergent series gradient expansion here at late times. So again, here I illustrate this concept within a MIS model. So here you see the same plot as previously, however, in the log linear scale. And for early times, the approach towards the attractor is constant, the rate of the approach, which in the log linear scale implies the power law behavior, right? The log of the power law behavior gives you a constant at the approach rate. In contrast, for late times, you have steeper and steeper approach to the attractor as the time progresses, and here you see that the time is goes quite far away to 100. So this means that this numerics illustrates those two mechanisms. At early times, there is a power law approach to the attractor. At early times, there is a decay of the non-hydro mode. This is not only the property of this MIS model. This has been observed also in other models, kinetic theory, but not in holography, just to mention. So assuming this, we can assume that a similar mechanism can be at work in QCD. And we can assume that since though at ultra-relativistic heavy ion collisions, the Bjorken symmetry is not exact, it can be still profound enough to have this early mechanism on. And these were our assumptions. So let me go back to this evolution. So now we want to connect the early time and late time evolution of the system by the means of the attractor. So you remember this energy conservation equation had this solution which drives our initial temperature to final state. And now we assume that we are always on the attractor. And despite this assumption, it's still not easy to determine this A star, which is the attractor. And so the assumption is that whatever the initial conditions we start with, they are dragged towards the attractor, they approach the attractor in such a small transient time that we can neglect this. So that's our approximation. So now let us see how we can utilize this to make a connection in between early and late time. So at late times, we have this Bjorken flow solution with the constant lambda, energy constant, which is determined by the initial conditions of the system. It's the only way initial conditions enter the late times. We also have the concept of entropy production. So much more interesting is the early time, and at early times, we don't know what the attractor is. So we have just adopted a parameterization of the early time attractor with the initial energy condition defined by mu, and this parameter beta, which determines the power law behavior. And this is translated to the pressure anisotropy of the form like that. So the pressure anisotropy essentially depends on beta. So now we have the pre-hydro evolution, which generates as the early entropy production. Then we can connect it to the entropy production at the hydro evolution, at the beginning of the hydro evolution. And since we can neglect entropy production during the hydrodynamics evolution, we can match it to the freeze-out entropy production. So now in this way, we can relate the final number of charged particles produced per unit rapidity to the hydro entropy, and in consequence to this initial energy deposition model. So now, but this depends on beta. So now we have a clear connection in between some parametric property of the early time attractor and the measurable quantity, which is number of charged particles produced. And in principle, and in particular, if we take the free streaming case, which is beta equal to 1, this power reduces to 2/3, which is the power from the pocket formula from Sorin's talk. Okay, so let me be a little bit more precise here. So our pocket formula reads like that. I hide these prefactors in this h of beta function because the way we are going to analyze the experimental data, this will not be relevant because we will take, say we'll take the Alice data as a reference point to fit the 2.76 TeV LED Alice data. So then we take, there are like 9 different centrality beams. So we are considering the ratios of this number of charged particles produced at mid-rapidity for different centralities. And then we can see that from our pocket formula, this unknown factor drops out. So the unknown part of the dynamics of this attractor drops out, and we are only left with the initial energy deposition model and this power law behavior Q, which is well defined. So now what we have done, and also because we are taking these ratios within one experiment, like here we have like 36 different ratios. We can also use the experimental error bars, which are quoted by the Alice group, and then we can make a chi-square fit of our beta to the experimental data. Now the fit, to make the fit, I still need to take some initial energy deposition model. So we have taken 3 models to see what comes out. So first is the dilute dense approximation. So in all of the models, we use the nuclear thickness functions, Monte Carlo Glauber probe defined. And the only difference is that the way initial energy deposition is expressed as a function of this thickness functions of the 2 incoming nuclei. So in dilute dense, you just compare at each point in the transverse plane, you just pick up the one which is, say, smaller or larger, and then you put the larger inside the square root and the smaller in front of the square root. Then we take also from the Trento family of models, we pick up one, which is with this parameter p equals to -1. Then the energy density is defined like this as a function of this thickness functions of these 2 incoming nuclei. And then we also take the dense approximation, which is simple product formula. Those C factors will drop out again because we take the ratios of the centrality beams. And then within these 3 models, for each of them, we make a chi-square fit to these ratios, and then we have some prediction for beta. So now the central point, is this plot. So here we have, I present you the 3 different betas which we have. So for dilute dense is 1.12, for Trento is 1.96, and for dense is 0.44. So here you see the lines which are produced by our fit. And also what is very astonishing, so this is the ratio normalized by the 20% centrality. That's the most stable one to present. So you can see that I can plot the same ratio for other experiments, and I can put this meaningfully in one plot. And you can see that this way of presenting data, that there is a universal behavior. I don't need to make this fit separately for other experiments. It's enough that I make it for one, which is our reference point, the lead collision and 2.76 TeV. And now we have a scan of other system sizes and collision energy, starting from very low energies up to top LHC energies of 5.44 TeV. And you can see that there is a universal behavior not only of the experimental data, but also fitted value of beta is matching the other systems in this way. So and this is also a meaningful way to compare all this data, because we are taking the ratio consistently always within one experimental data set. Okay, so let me discuss these results a little bit more in detail. So here you see again these 3 values of beta. So you can see that the closest one to free streaming is this dilute dense, is only 12% difference. But in principle, you can have the beta much different than what is expected from the free streaming case. And now what does it tell us? Obviously, it's not the beta of QCD, right? It's a modeling. So it tells us, or at least strongly suggests, that the pre-hydrodynamic flow is tightly connected to the initial state model. So you cannot just take, say, your favorite free streaming and try to match it with any initial energy deposition model. And also that the beta translates into pressure anisotropy by this formula, which I have quoted 3 slides ago. And now the corresponding pressure anisotropy is like 0.96 for dilute dense. It's negative for the Trento model. And in the dense, it's very large, it's 4.02. So this is the main message of this work, of this analysis. And in contrast, the free streaming, which is beta equal to 1, implies that the pressure anisotropy is 3/2, and the longitudinal pressure is 0. And it's so kind of what this results is pointing to is that it's not necessarily consistent to assume free streaming to be in line with any generic initial energy deposition model. So this little analysis that we did not only allows us to kind of constrain the properties of the attractor and try to extract the physical meaning of the attractor, but also it tells us that one should be very careful about trying to connect the initial energy deposition model with the start of the hydrodynamic expansion, and that there has to be a correlation in between models of the initial parameters of the initial state model and the pre-hydrodynamic flow, which is very important. And that the interactions are also important, because free streaming it means no interactions, but what the data is telling us is that interactions do play a role. So with that, I can slowly go to the conclusions. I still have like 3 minutes. So the attractor. So the first of all, the first point is that the attractor provides a simple conceptual link between early and late times. So using the hypothesis of the attractor and parameterizing what we were not knowing about the attractor, we were able to design a computation by which we were able to link early time behavior, pre-hydrodynamic flow with the final state observables. And then by looking at the experimental data, we're able to backwards constrain the initial evolution of the system. The second main message is that this tells us, this analysis, that free streaming is not necessarily compatible with a generic initial state model. That's I have already discussed. And that pre-hydro flow has to be matched with a specific initial state model that you want to consider. So there are not two independent things. It seems that they are strongly correlated and have to be considered together. So now, obviously, our computation is just initial. I mean, it's not the final answer, because we have made a lot of symmetry assumptions and other simplifying assumptions. So next step is to relax those, relax the conformal assumptions, which I were using all the time, relax the symmetry assumptions, so relax this Bjorken flow, 0 plus 1. So already a good step would be to consider true 2 plus 1 dimensional Bjorken flow, and then in a non-diagonal initial energy momentum tensor, this pre-hydro evolution. So in this way, one would use this model to increase the functional space of the Bayesian analysis, to make a full meaningful correlation in between the parameter of the attractor, like this beta, or perhaps any other parameter that we can come up with. We would have to really match this with all the other stages of this Hebbian collision evolution, perform the Bayesian analysis, and try to look for the results, for the correlations, and address more observables like mean PT, dependence on centrality, or the flow coefficients, and so on. So that's part of the future project of ongoing research to relax the symmetry assumptions and to make the Bayesian analysis possible within the extended functional space, where the free streaming is replaced by the hydrodynamic attractor. And also another approximation was that we are assuming that the generic initial conditions is rapidly dragged towards the attractor. Also, this is not necessarily the case. So this can be also, or should be tested within some models, how reliable this assumption is. And with this, I would like to conclude and thank you for your attention.
Thank you for a very interesting talk, Jacob. I see a couple of raised hands. Uli, do you want to unmute
Yes,
yourself?
this is very interesting. I must say I was really surprised about this universal scaling behavior that you found there, because the model that you're using for your attractor is based on pure Kane symmetry, which has no transverse flow whatsoever. And we know that transverse flow is essential to lead to the freeze out in heavy ion collision experiments, but it's not in any way included in your analysis. You somehow connect the final state with the initial state using purely longitudinal expansion, and still it seems to work and it seems to be universal. Do you have any kind of speculation or hypothesis or so why that why you find what you are finding and how that can happen in spite of the fact that you have ignored a key feature of realistic heavy ion collisions?
Oh, that's a very good question. I don't know if I have a good answer to that. Indeed, we're also kind of surprised that with this simplified model, we were able to get to this to describe this data. But this, if you would take more like transverse dynamics, would be well. Let me put it this way: we only address one quantity, observable quantity. So we would probably fail if we would like to address more quantities, which are more sensitive to the details of the dynamics. So that's for sure. But I don't think I have a good answer why it's works so unreasonably well. I mean, it's I agree. It's very surprising.
Thank you.
Next, we have Soren with a question.
Yeah, maybe before I ask my question, let me follow up on this a little bit. I mean, I think isn't at least one possible answer to that, I mean, essentially the observable one is looking at this entropy production, right? And that's happening early, where transverse expansion doesn't really play a big role, right? I mean, it's true that it's striking how much this is borne out in the data, and we were also very surprised when we see that. But I think that's I mean, that's one potential reason, right? Now, of course, if you look at anything that's energy related, you can convert, but entropy production is probably early, and then you would be less surprised. I don't know. Do you agree with this, Jakub?
Yeah, that makes sense. So essentially, the entropy and the particle production only happens at very early stages. As I said here, the hydro and the freeze out part, they do not contribute so much. So perhaps it has to be that's the reason why this observable is so good, because it's very sensitive to the early time behavior, where the system is determined by the non-equilibrium dynamics, and it's so. But still, it could be well possible that we would not get this universality. So what it's telling, at least I would, perhaps being a little bit bold, I would say that what it's telling us is that really some universal dynamics happens there at early times, because otherwise we wouldn't be able to get this description, because still we could have this strong sensitivity to the initial conditions that we are after.
Okay.
And essentially,
okay,
I would see no reason. I will let you speak in a moment. I would see no reason why we should doing a fit for like 2.76 TeV would be able to describe the 62 GeV data, right? But it happens to be the case.
Now the actual question I wanted to ask. So in the way you set up this, so you set this up, and you essentially somehow generalize our framework a little bit. You still assume that the whole equilibration or the whole non-equilibrium dynamics is essentially governed by one time scale. Is that correct? I mean, you say everything only depends on W tilde, and there cannot be another scale, right?
Yes.
Okay, but then, so then I have a concern, actually. So this then leads me to my comment, because I think this is actually then inconsistent with using this this dense formula for the energy deposition, okay? Because, I mean, the dense formula is based actually on physics that's happening at tau equal to 0 in principle, okay? Where you have actually field-like physics, okay? And this field-like physics becomes particle-like on a time scale which is set by 1 over QS. Okay, that's not linked to equilibration or interaction or anything at all, right? It's just later linked to the formation time of particles. Okay, so in that sense, so to say, from one power law at early times where your energy stays constant to then a free streaming regime, okay? And the value you get of 0.4 is probably somewhere in between of this also, okay? But there's another scale in the problem there, which is the saturation scale or the formation time of particles that sort of transitions you from one regime to the other, okay? And in fact, if you actually, I mean, if you take this into account, so if you go back to this formula, okay, and you assume that on a time scale which goes as the larger, or which goes as, I think, the larger of the two t's, okay, you transition from field-like to particle-like free streaming. You actually go back to this dilute dense formula, okay?
Okay.
So by essentially not doing one power law, but a polytrope with a second scale, okay, these two formulas are actually equivalent. So maybe this could actually be something interesting to explore if one, somehow looks whether there can or should be a second scale in the problem.
Yes, well, we have this scale of mu, the initial scale.
Yeah, but that scale doesn't enter anywhere. Right?
Yeah,
it doesn't enter as a time scale, right? It's just how much energy is there.
Yes,
right?
yes.
So what
yes,
I'm saying is there can be a second time scale. And in fact, really in the weak coupling limit, if you really go to dense, there should be a second time scale if you want to push this all the way to tau equals.
Yeah, sure, but we also make a conformality assumption, so we don't allow for this because the scale would break the conformality, right? This additional.
No, this has nothing. No. This just has to do with physics, right? It's just a statement that even in you go to weakly coupled QCD, this is a conformal theory, right? All I'm saying is that the entire equilibration, if you really want to push it to tau equal to 0, is not just determined by this omega tilde. There's another scale in the problem which is sort of set by the initial state, right?
Yeah, that's true.
Physics
that's true.
Going from field-like to particle-like.
That's true. And
I mean, it would be great if this could somehow, I don't know how to do it, right? But it would be interesting to see whether one could perhaps dig this out, right? Or whether you can include this in this kind of analysis.
Yeah, but also note that dense gives a very low beta, which I don't believe that would be anything true, and also very high pressure anisotropy. So that might be also indicating that it's not the right initial state model. So the closest, favorite.
No, but the point is you're taking this model and you're misrepresenting the physics. So then you're going to get an answer which is between extreme maximal pressure anisotropy and free streaming, because that's somehow what happens on that time scale. If you just do, if you were to actually do a weak coupling calculation. So I think the fit for dense is too naive, so to say. That's another way of saying this.
Yeah, and that might be the case. Yeah, sure. Yeah. I mean, as I said, so this is just tree representative, which we have considered, and there is lots of things to be done and generalized. Personally, my favorite is this dilute dense. It's closest to free streaming, but it's not exactly free streaming. It's very intriguing. You have only this.
Yeah, although with exact free streaming, it probably doesn't look much worse, right?
Yeah, it doesn't look much worse. Yeah, but the chi-squared fit, in any case, in all of the cases, we get quite good chi-squared fit. But I don't show it here because it's, well, as you said, the fit is, despite it works, is not like the final answer. I cannot claim it's the complete analysis of the experiment. However, this fit was quite narrow, and one was not within the error bar. So,
okay.
So yeah.
I think Giorgio has a question as well.
Hey, thanks. Yeah, it's a comment and a question. I mean, to me, the scaling is not so surprising from just a purely general consideration. The fact that limiting fragmentation applies in heavy ion collisions, which it experimentally does, at least at weak energy across different systems, makes a scaling like this pretty much inevitable. The question I have is, if you go lower in energy, I mean, it's related. If you go lower in energy at about the same time when some of the older people here might remember the kink and the horn and the step and stuff like this, which are probably related to changes in transparency, changes of how much entropy is carried by mu and how much entropy is carried by T. Have you tried putting in lower energy points from that region in that scaling plot?
I think not. What was the energy scale? You
7
mean
GeV or so, if I remember correctly, 5 GeV, 7 GeV. Data exists.
Yeah, for sure.
Star energy scan data exists.
Mhm.
Yeah, so it might be that this is simply, it's not just entropy, it's how much entropy is chemical potential and how much entropy is sort of, temperature. And if it's that, it will break, because if you look at the proton over pion ratio, if you look at the proton over pion ratio, it looks like a hockey stick. It sort of goes up very sharply at the low energy.
Mm-hmm.
And it might be that your scaling abruptly breaks down.
Yeah, that's possible. That's very, very possible. Yes, but then also in our assumptions about Bjorken flow and this mechanism would also not hold for very low energies. Right, so the lowest energy I see here is 62.4 GeV from cuprum.
Sorry, before Mike asks his question, some comment. If you go sufficiently lower in energy, you cannot take T temperature as your only dynamical variable. Yeah.
Yes, I need also chemical potential, right?
The whole thing breaks down.
Yes. Yeah, but it would be interesting to see how we can also say that perhaps some form of an attractor also is at work for lower energies. However, then you have to add more parameters and try to see how much this argument can be extended towards low density, so high density, low temperature phase of the evolution, and how equations, some form of equations of state would, or not quite equations of state, but how this finite densities would affect this argument and how it go through, how much it should be modified.
Okay, can I jump in with my question now?
I'm fine with that.
Okay. Yeah, very nice talk and very nice results.
Thank you.
A question on slide 11.
Slide 11 is this one.
Yes, this one. So conceptually, I have trouble with A Trento being negative. Doesn't that imply that we have opposite pressure anisotropy and maybe even PT is negative?
Yes. Yep, I think so.
That would be unusual, no?
Mm-hmm. Yes, that was surprising to us as well.
Why is it so different than, even in sign than the other cases, right? Because normally we would expect this number to be reflective of the small PL over PT, right?
Mm-hmm.
Attractor. So I just don't understand that number. If you can enlighten me, that would be great.
Again, I don't think I have a good reason or good enlightening answer to that. I don't have that much intuition about the Trento family of models. We have also tried other P's from this other parameters, but so this beta was quite high there, as far as I remember. I was never close to free streaming, but it did not vary that much over as we changed P. But this, I don't have a good intuitive reason to see. I was expecting an instability here, but as you mentioned yesterday, it doesn't have to be the case.
Yeah. So I guess a question for you and maybe the audience, is that something that's used in phenomenology? Is people use this P-1 Trento?
I think the Bayesian
analysis excludes it. Yeah.
I think it's P equal to 0, which is
right.
Yeah. Bayesian analysis. Yes.
So it has the wrong fluctuation spectrum, but this is not about fluctuations here. So
yeah. So that's why I say it's very important. Will be very important to include this parametric attractor. So parameterize the attractor and then include it in the Bayesian analysis, because then it would really enlighten us about how how this beta parameter would correlate with other parameters used in the description of the heavy ion collision. And that for me it's very very exciting thing to try to do.
I agree. It's all exciting. Maybe I just don't know what the physical interpretation of that is.
I also don't have one. But well, I also think I am also wondering how much those numbers can change if we include the full more complete picture of the events and more complete analysis. I'm kind of convinced that those might change.
I have another comment. This sort of came out of the discussion. As I only said, we're not talking about fluctuations here right now, right? But I mean, actually, one important thing about this is also and you in a sense have this in your formula where you write the energy density, or where you write what's the multiplicity that comes out in terms of the energy density, right? I mean, one of the points is once you include this map between initial state and sort of what goes into the hydro, right? Whenever you change this attractor curve or you change its limits or something, this also changes the fluctuations, of course, right? So it kind of changes the amplitude. It also will, so it will change fluctuation properties as well when you vary this. So that's just a comment.
Yes.
So that's in principle another handle that also goes hand in hand, right? So again, initial state model that gives you some fluctuations, and how you propagate them again will change the properties.
Yes.
So I think
I have another question since we're on this. So it's very beautiful that you find that you can extract this beta that by pulling it out of the formula that's at the top here, right? And then using the fact that it's out front to cancel it in the ratios. But I guess in the real world, it could be true that H of beta or beta itself could depend on centrality, right? So that somehow the dynamics of a very dilute collision, of course, is very different than a head-on one, right? But that would break your factorization in this case, right?
It would, yeah. So in principle, well, beta, I don't believe it could be, well, at least according to our interpretation, it should not depend really on centrality. However, there is tau zero entering this factor, all right, this H of beta, because otherwise the dimensions don't work. So it's tau zero to some power, and then we assume that tau zero is independent of centrality, which was kind of the assumption we have seen in the literature. But if you would assume that tau zero also depends on the centrality, which is essentially a physical assumption, it should, right? Then this factorization would break down, and would have some additional.
I mean, the fact that it works is kind of evidence that the factorization occurs.
But the universality of this ratio kind of supports this assumption, right? Just by looking at the experimental data. I mean, yeah.
All right, let's thank Jakub one more time, and all our speakers from today. I think we have a few more minutes to discuss if we had